Hello everyone, my name is Kavit Shah. I'm currently enrolled as a master's in computer science student at Rutgers University. Today I'm going to talk about a classification technique which has been widely used in machine learning, which is known as the linear discriminant analysis. Linear discriminant analysis, or LDA in its most basic terms, could be defined as a data classification techniques which could most efficiently and effectively be used for dimension reduction and data reduction, and could be also used for extracting the primary features. LDA, despite of its simplicity, often produces robust, decent, and a very well interpretable classification of the datasets which we are given in hand. So the linear discriminant analysis method of classification has been around for quite a long period of time, but it was first formulated by Fisher in the year 1936, which was based on the classification into two classes, and it was later refined by others in order to generalize it into multiple classification method. So in the most basic terms, we could uh, we could consider LDA as a method for searching the best linear combination of variables which would be used to classify the given data set into two classes. This is just a picture of classification into two classes for a data set which has been given based on two dimensions, busage and days del Q. Based on the Fisher LDA's method, we are constructing the best possible estimated line and then dividing the data set. So before we move on from the logistics and methodologies of the working of LDA, it would be quite imperative to understand what the problem that LDA would help to answer, which we could quite efficiently do with the help of a simple example. Suppose a cancer medical center has devised a new medication drug for treating cancer patients. However, during the trial, it has been observed that the drug is only being effective in treating certain patients while it is adversely affecting some other patients. So it is a dilemma as to who should be ideal in order to give this drug to. However, they have a trend which shows how the drug performs on patients with different transcription levels of genes, where transcription levels is basically an RNA version of the particular gene. So as can be seen in the figure below, the single axis shows the transcription of gene X from fewer to higher transcription, and the green portion shows the people whom the drugs works on, and the red shows the people whom the drug does not work on. And we could clearly see that for fewer transcription, the drug works for most of the part, and for higher transcription, the drug works does not work for most of the part, while there is an overlap in the middle. So this is not an efficient method of classification, and we could do better. We have just used one gene X. What if we make use of more than one gene? Say, what if we use two genes? So let's take an example for two genes, gene X and gene Y, which we could show based on a 2D plot. So as we can see in the plot here, this demarcation or separation line as formed by the LDA method is doing a better job than just considering one gene in into separating the data sets into two particular sets of classification. So what if we make use of more than two genes even? What if we use say 10,000 genes, say 20,000 genes, or some XY value? Then we could even do a better job in classifying the data set into classes, right? But this is not feasible in order to visualize when we are given higher dimensions. So what is LDA, and like why is LDA useful? We had PCA which could be used to reduce the dimensions of the data set into just the genes which are giving the most variation, or the eigenvectors which were giving the most variations, right? However, the use of LDA lies where we need to maximize the separation for making efficient decisions, right? We want to separate the categories so well that we are we are able to categorize any given data set into a particular class, for which LDA is very useful. Now we look into the mathematical formulation for devising the LDA model as given by Fisher, which is used for categorizing data into two classes as stated. So the Fisher model would basically be looking for a sum of to represent the data set in the form of linear combination of variables as given by this here, where B1, B2 or beta 1, beta 2, beta 3 are the estimated coefficients which we need to estimate. So and choosing this estimates in such a way would be useful for the LDA method, that it maximizes the distance of separation between the categories and it minimizes the in-class variance. So for a particular class, the particular data points in those should have a minimum variance. So from this, we can say that the value of the uh, estimated coefficients, that is beta, would be of the order of the difference of the mean between the two classes, that is mu1 minus mu2, divided by the pooled covariance. C inverse is the pooled covariance, which is basically the weighted average pooled covariance, which is the weighted average of the covariances of the two classes. So C1, C2 are the covariances for the two classes, and this basically represents the pooled covariance or the weighted covariance. Now, let us take an intuitive understanding into what the Fisher's LDA method basically is. So suppose we are given n samples. We are given n samples, of which we need to divide those samples or data points into two classes, say C1 and C2, and this class C1 contains n1 data points and the class C2 contains n2 data points. Then if xn is the sample which has been given to us, then we need to find a best estimate, say w, which would be basically the estimated value of the coefficients which we looked into previous slide, beta, such that we would project the data points x on the line w. So the new data points after projection would be w transpose x, correct? Then suppose the mean of the classes C1 and C2 were suppose mi initially, then after the projection, the mean of the classes would become W transpose into mi, which is the same as we did for the uh, calculating the data points in the first point here. Um, now, now we make use of a scatter matrix in LDA, which is basically an estimate of the covariance matrix, which is uh, basically a D by D. If suppose we are given D dimensions, then it would be a D by D matrix. It would be a positive semi-definite matrix, which would be showing what the correlation is between each data points in that particular class. So we would be making use of two scatter matrices in LDA method. One is SB, which would show the measure of the distance between the class means, and SW, which would show the measure of the spread around the means of each class. So this supposes the mean of one class and this supposes the mean of another class, then the distance between these two means would basically be interclass variance or between class variance, SB, and the variance between particular data points of a particular class would show SW, which is the spread around the means of each class. Correct. Now, assuming that we are clear with with the intuitive understanding, we would go ahead with formulating it mathematically. So, what the Fisher's LDA method basically wants to have is it wants to estimate the coefficients W as a function JW, such that it maximizes the difference in the mean. It maximizes the difference in the mean between class scatter, and it minimizes the variance of the within class scatter. Correct. So in order to understand this better, we would be writing this numerator term in terms of W W, that is W vector, that is the coefficient of the LDA's estimate. So we could write M1 as we calculated in the previous slide as W as this term, and then taking W transpose out from each of the terms, we would basically be getting the equation 2, which is shown here, that is W transpose SB W, where SB is the between class scatter. Now we would also be liking to change this S1 square plus S2 square, which is the denominator term, in terms of W as well. So what we could write SI, or the class scatter before projection, would be, which is basically the formula for the calculating the covariance matrix, which would be summation of xn minus mi into xn minus mi transpose. And after the projection, since xn's become w transpose xn, so we would be getting the scatter for the projected samples as this term here, and it's simply squared term, where mi small mi would be replaced by big Mi, which is the mean after the projection. And if we rearrange this, like taking W transpose common from each of these terms, we would basically be leading or arriving SI square as W transpose SI W. So basically S1 square plus S2 square, which is the denominator term, would be given by W transpose SW W, where SW here is the within class scatter. Now that we have both the numerator and denominator in terms of W and SW and SB, that is the within class and the between class scatters, we would write JW as WT SPW divided by W transpose SWW. So we basically want to maximize this based on W. So we would differentiate it with respect to W and equate it to 0, and we would basically be landing on this term here, which could be used for finding the coefficients W. This is a simple eigenvector problem where V is the eigenvalue and W would be the eigenvector. So now, what are the main things that we need to compute beforehand in order to estimate the coefficients? Mean vector, which is basically mu. Mu would be given as the average of all the data points within that particular class. The mu1 is for class 1, mu2 is for class 2, and so on. Sorry, not the class for the particular dimension. So mu1, mu2, etc. are the mu's for the particular dimension. Then we have the covariance matrix. Which would basically be computed for a particular class given by summation of x minus mu x, y minus mu y divided by n, where mu x and mu y are the mean values for that particular class. Group probability, we could write group probability as probability of group 1 would be the number of data points in that group divided by total number of data points, and for group 2, the number of data points in that particular group divided by the total number of data points again. So now what could be a metric which we could use for accessing or assessing how the LDA method is performing? So one of the effective estimator which we could use is the Mahalanobis distance, which would be given by square root of these delta square term. So delta, which would be square root of beta transpose mu1 minus mu2, where beta transpose is the transpose of the estimators which we got using the LDA method, and mu1 minus mu2 is basically the difference in the means of the two classes. Now, in order to assess how the LDA method performed, which we could see that if delta is larger, then the LDA method is performing well and it's separating the two classes ideally. Suppose we have the delta greater than 3, then it would mean that the standard deviations overlap between the group is quite small, and that there is a low probability of misclassification. So we would have very less overlap. Now we would consider a simple example which we shown in the first slide, and try to formulate the LDA parameters and see how they perform. So this is basically a data set from the bank, which is regarding a small business clients who defaulted, which is given by the red square, and who did not, which is given by the blue circle or the yep. And by separated by the delinquent days, that is day del Q, and the number of months in business, that is the busage. We would use LDA to find the linear model, which would be best separating these two classes, default and non-default. This is basically the data set sample which we are given, classified into no or yes for non-default and default. So for LDA method, the first step would be to calculate the means, calculate the covariance matrices, and the class probabilities. So we could easily compute the mean, the class probabilities, the covariance matrices using the formula which we had here, the four formulas which we had here. So computing those values, using those formula. Now we got the individual covariances. We would also want to compute the pooled covariance matrix in order for estimating the parameter in the formula. So it would basically also be computed simply by using that formula before. And now we could go ahead and compute the model coefficients or the estimated coefficients, which would be C inverse time mu1 minus mu2, where C inverse is the inverse of this pool covariance matrix, and mu1 minus mu2 is basically this term, mu1 minus mu2 for busage and mu1 minus mu2 for the del Q days. And we could also compute the Mahalanobis distance by using the formula before, which comes out 0.32. So LDA is quite useful in this example, because we got the Mahalanobis distance as 2.32. So the so we could say that it fairly effectively classifies the data set into the two classes without much overlap. Now, what if we have given a new point and we want to classify it based on the projection, so that we could maximize the separating distance between the classes, and we want to classify it as a group one, suppose. Then there is a simple formula which we could use, which is beta transpose times x minus bracket mu1 plus mu2 divided by 2, where mu1 and mu2 are the mean for the two classes. Beta transpose is the estimated coefficients which we got using the LDA method, and x is the new point. It should be greater than minus log probability of group 1 divided by probability of group 2. If this inequality holds, then we could classify it as group 1. LDA example prediction. So suppose we are given these points, and we compute this for all the points here, and z score is basically putting in the coefficient that it's basically the linear combination beta 1 times x1, beta 2 plus beta 2 times x2, and so on value. That is the z score. And we are predicting based on the LDA method these points as this, while the defaults were this. So we have two errors, which is not bad, and it's fairly effectively being classified for the two classes with some error, of course. So we looked into the linear discriminant analysis for two classes. However, what if we want to distinguish it for more than two classes? So we could extrapolate the formula which we had for the Fisher LDA method for two classes into more than one classes, where suppose we are given we are given, suppose any, say, a number of classes, and we want to compute the data set. We want to compute the classes for the data set into those a classes. So we could use a simple formula yk of x, that is the um, z value, or the we could say is the score function, as -1 by 2 x minus mu k transpose c into ck inverse into x minus mu k minus half ln mod ck plus ln probability of group k, where where um, we could see that ck inverse here, or ck, is basically the covariance matrix for that particular class. We are computing that ykx value for that particular class. So ck is the covariance matrix for that particular class, right? Mu k is the mean value from all the data points in that particular class. Mod of ck here is the determinant of that covariance matrix for that ck, that is the kth class covariant matrix. And probability of group k is basically the prior probability of kth group, which we could give as number of data points in group k divided by the total number of data points. And the compute for a particular x, we would be computing the z value for all the classes, and the class which gives the highest z value, we would be simply classifying the data points based on whichever class has the highest z value. And the Mahalanobis distance from x to mu could also be given for this quadratic LDA as x minus mu transpose times C inverse times x minus mu, where x is the data points, mu is the mean vector, and C is the pooled covariance matrix. So let us summarize what we learned about the linear discriminant analysis method. Linear discriminant analysis is an efficient method for classifying the data into two classes, and it could also be generalized into multiple classes as well, as we look towards the end of the slides. It is a simple, mathematically robust, and it would often be producing very good accuracies before we even go to the complex methods which have been discovered in the model world. So so that should be it for the explanation for the LDA method. Hope you like this video. Thank you so much for watching. See you again. Bye bye.